we have been struggling within this industry to get a holistic picture of software systems for decades. So I would like to start by having a look at one of the classic approaches to attacking this problem, and then we see the limitations of that before we move on. All right? So how many of you are using complexity metrics on a daily basis today? It's just a few of you. All right. So I think you're well aware of the different complexity metrics we have. We have a... Yeah. In the meantime, have a look at the McCabe cyclomatic complexity metric. McCabe cyclomatic complexity works like this. You consider your program or your function as a graph, and then you calculate the number of possible paths through it. And the higher that number, the more complicated your code. And McCabe cyclomatic complexity is really just one out of a bunch of different metrics, and they all work the same. We take a program, a complexity metric tool, throw it at our code base, and out comes a prioritized list of each module with a complexity number assigned to it. So that's wonderful. That lets us identify the most complicated code. So if we have those complexity metrics, why don't we use them more in our industry? I don't know. But I know why I don't use complexity metrics. The reason I don't use complexity metrics is because complexity metrics are pretty bad at predicting complexity. Perhaps a bold statement, too, so please allow me to support it. I would like to read a quote for you. Syntactic complexity metrics cannot capture the whole picture of software complexity. And the interesting thing about this quote is that it's from a research paper. And what the researchers did here was that they looked at these different metrics, McCabe and Halstead, and looked how well they performed on real-world software systems. And what they found out was that as soon as they started to control for the number of lines of code, those more elaborate metrics didn't add any further predictive value. Wow. The number of lines of code? I mean, that's a really lousy metric. Is that the best we can do? Let me read a second quote for you. And this is one of my favorites because it's a little bit evil. The use of metrics to manage software projects has not even reached a state of infancy. And this is a quote by Robert Glass. And what Robert Glass means is that software systems, they are just so large and complex that there's no way we're going to be able to measure them. So what Glass suggests instead is that we rely upon our intuition. Now, as some of you may know, I actually have a parallel career as well. I have a parallel career within psychology. And as a psychologist, you just have to love the concept of intuition because it's such a warm, fluffy human subject. But what is it actually? What is intuition? Well, let me tell you. How many of you have been working in the software industry for more than 5 years? The majority of you. More than a decade. 2/3. Great. So you've all been working for a long, long time doing software development. And over those years, you have all built up a lot of expertise. And that expertise is stored away somewhere in your head. And now, intuition, that's basically just something in the situation, perhaps something you see on screen or something you see in your favorite code editor that triggers a recall of some of that information. So intuition is basically just recognition. The trick with intuition is that it's an unconscious automatic process. And that means you don't have any conscious control over what kind of information that gets retrieved. And that's what gives intuition its mythical qualities. But it also makes intuition extremely sensitive to cognitive biases. And even if we could somehow control for those biases, which we can't, but even if we could, intuition still wouldn't do the trick. And the reason for that is that intuition doesn't scale. No matter how good programmers you are, there's no way your intuition or expertise is going to scale to hundreds of thousands or even million lines of code. And this is why I suggest that we look into a radically different field for support. It's a different discipline, but one that faces similar, open-ended, complex questions as we do. So welcome to forensic psychology. You probably all know a little bit about forensics. Perhaps you've read about it in the news, or you have been watching CSI. And I also bet that all of you have seen the movie Silence of the Lambs, right? Yeah, cool. I also bet that all of you agree with me that Hannibal Lecter is the coolest character. Great. The first time I saw that movie, I was quite influenced by Hannibal Lecter. And I don't mean that in a scary way, right? I was influenced by his forensic skills, not the other stuff. It's completely safe to have dinner with me tonight. I'd hate to eat alone just because of that little slip. Because it's actually quite fascinating what Hannibal Lecter does. Look at it. Hannibal Lecter, he sits there locked up in his cage, and he receives information from the crime scenes. And based on that information alone, Hannibal Lecter is able to deduce not only the motives, but also the personality of the offender. And the first time I saw that movie, I was like, wow, I want to learn to do that. Years later, as I studied criminal psychology, I got terribly disappointed. Because it turned out that all those techniques that Hannibal Lecter had been using, they have a serious limitation. It turns out they only work in Hollywood movies. But fortunately, we got some more scientific methods. So please allow me to give you a 2-minute introduction to geographical offender profiling. Geographical offender profiling is based on a very fundamental fact. And this fact is a bit surprising, perhaps because it's so obvious. But did you know that criminals, most of the time, behave just like us? They go to the movies, they go to restaurants, they go shopping, they visit friends, perhaps they even pick up the kids from school. And as they move around in an area, that's where they spot opportunities for crimes. Because for crime to occur, there has to be an overlap in time and space between an offender and a victim. And that's important because it means that the crime scenes, their geographical locations, are never random. They contain information about the criminal. And that's something we can use to catch them. So let me show you how this looks in the real world. This is a map of 19th century London, the Whitechapel area, the streets that Jack the Ripper haunted. And you see those blue dots? Those represent the crime scenes of the Ripper. Now, if we want to catch the Ripper, here's how we do it. We consider each crime scene a center of gravity. And then we weight them all together, but with one important psychological twist. Psychologically, all distances aren't equal, so crime scenes that are closer to each other tend to get assigned more weight. So now, when we weight them all together, we end up with a new center of gravity. And you see that red area there in the middle? That's our hotspot. And according to the research, there's a 70% chance that our criminal will have his home base there. So if you want to catch the Ripper, that's the area to patrol and supervise. Now, I guess you're all wondering, all right, but how is he ever going to tie this back to software? Guess what? I'm a bit curious myself, so let's have a go at that. But before I do that, Jack the Ripper, it's a really cheap case study to make because the Ripper, he was never caught, was he? So who was he? Perhaps we want to find out in order to know if this stuff works at all before we build on it. I really don't know who Jack the Ripper was, but what I can do is to look at the main suspects and see how well they fit the profile. So let's start with my #1 favorite suspect, Mr. James Maybrick. James Maybrick was a cotton merchant from Liverpool. And when James Maybrick went to London to do business, he used to rent a room in Middlesex Street. So let's have a look at Middlesex Street on our map. It's there, right in the middle of our hotspot. So James Maybrick is a pretty good fit for this profile. If you read the news like a year ago, you probably heard about the supposed DNA evidence against another Ripper suspect, the hairdresser Aaron Kosminski. Kosminski most probably lived at Zion Square. So let's have a look at Zion Square. Zion Square is there, a little bit east of the hotspot. So Kosminski is not as good as a fit as Maybrick. But this just raises a really important point that you need to keep in the back of your head as we transfer this to software. That a geographical offender profile never ever points to a precise position. What a geographical offender profile does is that it projects a probability surface onto your geography, right? So, how does this relate to software? Well, think about it. Look at what we have done. We have taken a potentially vast geographical area and narrowed it down to a much, much smaller area where we can now focus our human expertise. What if we could do the same for software? What if we could take those million lines of code and narrow them down to some smaller, manageable hotspots? That would be a huge win. So, how can we use this in code? The first thing that we need is a geography of code. Here's my favorite approach. Welcome to Code City. In Code City, software systems are visualized as towns. Each namespace, each component is visualized as a city block. And each class, each module is visualized as a building. And the larger that building, the more complicated the code beneath it. And what I like about Code City is that it gives us an excellent way to reason about the complexity distribution in our software system. You see those big buildings? Those are clearly the ones that are the hardest to maintain, aren't they? I would claim that this information is incomplete. And it's incomplete because complexity has this property that complexity is only a problem when we have to deal with it. If those large buildings represent code that's been stable for 5 years, that works wonderfully in production, and that we never ever need to touch, well, they may still represent a problem, but we probably all have much more urgent matters to attend to. Where are those matters? To find out, we need to add the missing dimension. We need to add the spatial movement. Not of criminals, but of programmers. And it's data that you all already have. We're just not used to think about it that way. I'm talking about our version control systems. Let's have a look at that. Here's a simple example. It's a commit from Git. And you see that each time we make a commit, a lot of valuable information gets recorded. We see who did the change, when was the change done, and most importantly, where in the code did the change took place. Now, this represents a single commit by a single programmer. A large system consists of virtually thousands of commits. So what if we take all those commits, aggregate them, and project them onto our geography of code? Here's what it looks like. You see those red spots glowing up? Those are hotspots. And in this case, a hotspot represents complicated code that we also have to work with often. Now, what kind of code will we find inside a hotspot? To answer that question, I decided to do a case study. And this is a case study done on a fairly large system consisting of 400,000 lines of code. It was developed by 89 developers, and I looked at a period of 1.5 years. And during that time, those developers made a lot of changes. Here's what a geographical offender profile looks like. my wife claims that it looks like an alien, but it's not. This is 400,000 lines of code. And you see that I moved back into a two-dimensional representation. And that's because I think that gives me a better overview. And it's also a bit more reminiscent of the geographical offender profiles we looked at earlier. Now, this is an interactive visualization, so you can zoom in and out to the level of detail of interest. But even here, on the highest level, we're able to spot a number of hotspots. Remember, hotspots are complicated code that you have to work with often. So what kind of code is that? What happens when we look into a hotspot? What will we find? I set out to answer that by mining a second set of metrics. I looked at the bug distribution in that system. Because, you know, bugs have this really fascinating property that they tend to cluster. They like each other. So relatively few modules are responsible for most bugs. And what I found in this system was that the hotspots predicted 7 out of the 8 most affected parts. Even more interestingly, the hotspots only made up 4% of the code, yet that code was responsible for 72% of all defects. Or, put another way, in this particular system, if you improve just 4% of that code, you get rid of the majority of all defects. And what the hotspot analysis does for you is that it points you to those parts of the code that matter the most right now. So, this is a very good starting point, but it's really just that. It's a starting point, and we can do so much more with this data. So let's have a look at that by considering the evolution of a typical program. Now, what you see there is a picture of a Python program. And I'm well aware that you cannot see the details, and that is deliberate. I just want you to focus on the overall pattern here. Because I'm fairly convinced that we as an industry, we're actually quite good at writing code. We all know what good code looks like. We know about cohesion, we know about low coupling, we know about the solid principles and all that other stuff that we think is important. So, our first version of a program typically looks quite good. But let's see what happens next. Whoops. It got a bit stained. Oh no. Oh. That doesn't look like a good thing, does it? Oh no. What just happened? Our program started out so pretty, and then a number of small disasters occurred to it. What are those disasters? Well, let me tell you. This one is a new feature. That one, that's a bug fix done late one Friday, just before a deadline. And that has to be when the project lead decided to cut the scope. And then, of course, he changed his mind. So this, my friends, this is basically just time happening to your program. This is maintenance, and that's actually a good sign. Because it means someone cares enough about your program to suggest changes to it. You have probably have users. Congratulations. The problem starts when we allow that trend to continue, when we build upon a shaky foundation, when we allow our programs to decline in quality. So, what if we could use the same version control data to identify programs that decline in quality like that? Here's how it looks. And this is actually some real data as well. This is from the open source project Mono. And this is an analysis I call complexity trends. And what I do here is that I look at the source code repositories. For each hotspot, I scan the source code repository and fetch the historic version of that hotspot and measure the complexity of each historic version. And that allows us to plot a trend over time, which in turn allows us to project a trajectory into the future. Now, the example you see here shows the complexity trend of a single hotspot over a period of 4 years. And you see that during that time, that code has kept accumulating complexity, it becomes worse and worse over time. Now remember, it's a hotspot because it's code that we have to work with often. What do you think happens if we have to work with a piece of code often and that code becomes more and more complicated? It's not a wonder that there's a strong correlation between hotspots and defects. So this is another example of the kind of value we can get out of the history of our code. But we can do so much more. We can investigate a completely different dimension of software development. We can investigate the social dimension. And this is important because software development is about much more than technology. Software development is also a social activity. And I'd like to introduce this part of the presentation with one of the best observations I know about software. Code doesn't lie. If we want to understand how something really works, we need to look into the code. Because the truth is there, and it's described in very precise technical detail. So, code doesn't lie, but it doesn't tell the whole truth either. And if we limit ourselves to what's visible in the code, we miss a lot of valuable information. And I would like to show you an example of that. This is an analysis called temporal coupling, and temporal coupling is something you cannot measure from code alone. Here's how it works. This is a simple software system consisting of just 3 different modules, and you cannot read the name of either one of them, but I will walk you through it. So, the first time we make a change to the system, we change the fuel injector and the diagnostics module together. The second change we make, we're changing something else. In the third commit, we're back to changing the fuel injector and the diagnostics module together again. Now, if this is a trend that continues, there has to be some kind of relationship between a fuel injector and diagnostics module, because they're changing together over time. What kind of relationship could that possibly be? Well, when you start to investigate those cases, what you find most of the time is this. You have some code over here, some other code here. This code uses that code, and each time we change the API, we have to change the client as well. So yeah, this is just plain old physical coupling. And that's indeed something you can measure from code. But remember, temporal coupling isn't measured from code. It's measured from the evolution of your code. And that means you will sometimes find cases like this, where you have 2 modules, there's no dependency between them, yet they keep changing together over time. How can that be? Is it some kind of spooky quantum physics thing? No, it's not. What I find most of the time when I investigate those cases is a dear old friend. Copy-paste. You have some code over here, you copy-paste it here, here, and here, and now, each time you modify the original, you have to remember to modify the copies as well. So, temporal coupling is a great tool to detect software clones. But we can do so much more with temporal coupling. We can use it to analyze complete software architectures. So let me show you an example of that. You have a software system here consisting of 3 different subsystems. And we can measure temporal coupling on a subsystem level as well, and we see that there's indeed a coupling in time between those 3 subsystems. Now, a question for you. How many of you think it makes a difference if those 3 systems are in the hands of a single programmer, or if they're developed by multiple programmers on multiple teams? Is there a difference? Oh yes, it makes all the difference. And I actually experienced that a while ago. So please let me share a story. This happened some years ago. I did some work for a fairly large development organization. And there were a number of 100 programmers. And the first day I got there, I got assigned a number of tasks. So I went to my computer and started to do one of the few things I do well. I started to write code. And after a while, I noticed that I had to do a change to an API. It was a really, really tiny change. The problem was just that API was owned by a different team. So I walked over to their team lead, and I asked him, sorry, but do you think you could make this tiny change to this API? And he was like, yeah, sure, it's a simple change. So I started working on it right away. Oh, perfect. I walked back to my desk, and I picked another task to work on in the meantime, and that was good. That was good because it took me 1 week to get that tiny change done. I didn't think much about it at that time, but it turned out we had to modify that API a lot. And every time we needed a change to it, that change took at least 1 week. So one day, I figured I really have to find out what's going on here. So the next time I asked the team lead, I mean, sorry, but was the change harder than you expected? And he looked at me like I was completely stupid. No, I mean, seriously, I told you it was a simple change, so why do you ask? I mean, yeah, but it took you a week. And what he told me completely changed how I view software architectures. It turned out that it was indeed a trivial change to them. But in order to do it, they had to modify yet another API, and that was owned by a different team. And that team, in turn, had to go to yet another team. And that team had to go to a database administrators. And as we all know, that's where all change requests go to die. So it turned out that if you have a dependency in time between different software systems, and those software systems are developed by different people, then guess what? You don't only have a dependency between software, you have a dependency between people too. And this goes all the way back to one of the famous observations on software, Conways Law. And Conways Law has received a lot of attention over the past years. So how many of you are familiar with Conways Law? Like half of you? All right, so let me give you a brief introduction. So Conways Law is basically the observation that the way we are organized, the way we as people are organized, tends to be reflected in the kind of software we design. Now, the cool thing with Conways Law is that it has just as many interpretations as there are research papers about it. So we can basically just pick the interpretation we like, the one that supports the message we want to carry. So I tend to choose Conways Law in reverse. And I like it because Conways Law in reverse means we start with the system we are building. Given a proposed software architecture, how should we organize in order to make this happen as efficiently as possible? And what I like about Conways Law in reverse is that it's an excellent organizational tool. But, I mean, most of the time, we aren't doing new software architectures. We have existing systems that we need to improve, that we need to continue to add features to. How can we use Conways Law on legacy code? My recommendation here is to start with what we have today. To understand and measure how well does your current architecture support the way you work with it today. And from there, you can start to improve. So, how do we make that analysis? Here's one way, and this is something I call communication diagrams. Communication diagrams are measured from the evolution of a code base. So here's how we do it. You basically scan your source code repository, and each time you find two programmers that have worked on the same parts of the code, those two programmers get a communication link between them. Now you continue to scan, and along comes a third programmer, and if she has worked in the same parts as the other two, she gets a communication link as well. And over time, this allows us to build up a graph over the ideal communication paths in our organization. And I say ideal because those are the communication paths reverse engineered from how the code was developed. there's absolutely no guarantee that they represent communication that actually took place. For all we know, those people could be located in different parts of the world. So what you want to do once you have a communication diagram is to compare it against your formal organization. And any discrepancies have to be understood. Now, when you do that, what can you expect to find? According to Conways Law, we should strive for something like this. You have 3 different teams here, and you see that most communication paths are within people on the same team. And that's a good sign, because it means each team, they work on approximately the same parts of the code base. They share the same context. And this is something that just makes communication so much easier and cheaper. And you also see that you have the occasional programmer that works in a different part of a code base. And yeah, that may also be a good sign. Cross-pollination is a good thing for software teams as well. So this is where you want to be. Let's look at the opposite side of the spectrum. Let's look at a complete disaster so that you know what to avoid. This is a story about a company. And this is a company in a good position. They were going to do a new product. And they were in a good position because they had done something very similar in the past. So they knew this will take approximately 1 year. Of course, someone came up with the idea that, yeah, 1 year, well, but we have this really cool trade show coming up in just 3 months. Can't we do it in 3 months? How do you take something that's expected to take 1 year and compress it down to just 3 months? Easy. Just throw 4 times as many developers on it. And this was a fast-paced project, so in shorter time than it would take you to read the Mythical Man Month, this project was manned with 25 consultants. And you should organize those people in 4 different teams. How do you think their communication diagram looked? This is the real data in all its gory detail from the real project. Looks kind of cool, but let me assure you, there's nothing cool about it. This is a complete disaster. This is chaos. This is anarchy. I mean, sure, the people within each team, they seem to work on the same parts of the software. The problem is just that everyone else does that as well. So this is not 4 different teams. This is virtually one giant team of 29 developers with artificial organizational boundaries between them. And I didn't work on that project myself, but I did some post-mortem analysis and talked a lot to the developers. And they told me a lot of interesting things. The first thing that everyone said was that they had a lot of defects. They had a lot of bugs. The second thing that they complained about was that the code was hard to understand. Because think about it, even if you wrote a piece of code yourself today, 3 days from now, it looked completely different because 5 other developers had been working on it in the meantime. And finally, and I think the most interesting thing they told me was that they spent a lot, and I really mean a lot, like in days, on merging different feature branches. And if we look at the communication diagram, we see that no, they didn't have a merge problem. They had a problem that their architecture just couldn't support that many people working on it in parallel. And when you find yourself in that situation, there's really just 2 things to do. Either change your architecture to support the way you want to work, or change your organization. So please, align your software architectures and your organization. Your code is going to thank you for it. All right, remember the project I just told you about. The developers complained a lot about software defects. And this isn't really surprising given what we know about the relationship between defects and the number of programmers. It turns out that the more programmers behind a module, the more quality issues in that module. So I started to think, well, can't we mine that data from a version control system as well? Of course we can. Here's how it may look. So this is a visualization called Fractal Figures. And it works like this, that you consider each module a box, and each programmer gets assigned a color. And the more that programmer has contributed, the larger their area of the box. So you see an example of 4 different modules here, and you immediately see that the red and the green developers, they have made most of the contributions. Now, if we're after modules that suffer excess parallel development, this is the one we would go after, because it has contributions from many different programmers. And when you see a pattern like that, you need to understand why. And when you start to inspect that code, what you will find in most cases is that code changes for a reason. The reason that code attracts that many developers is probably because it has many reasons to do so. It has too many responsibilities. So this is a really useful way to identify code at risk for defects, but we can do so much more. Fractal Figures gives us an excellent way to spot the main developer behind each module. It's kind of like the knowledge owner. The developer who has written most of the code probably knows the most about it. So if you have that information for each module in a system, what if we take that information, aggregate it, and project it onto a static surface of a code? That would allow us to build up a knowledge map. Here's what it looks like. And this is real data from a real project. This is the Scala project, a part of the compiler. And I'm not sure if you can read the labels, so I read them out for you. But this is something we developers use to facilitate communication. For example, say that you join the Scala compiler project and you want to know something about the backend. Or you're planning to do a code review of part of the backend. Well, I would say it's a fairly good guess that the light blue developer knows something about it. And if she doesn't know, perhaps the green developer knows. So this is a useful communication aid to developers, but we can do so much more. We can aggregate individual developers into teams. And when we do that, that gives us a way to evaluate Conways Law. Here's what it looks like. You see, we have 3 different teams here. And from the perspective of Conway, this actually looks quite good. You see that the red team, they pretty much have their own subsystem. The pink team, they also have their own subsystem. But down here, we have a large system with contributions from 3 different teams. And again, when you find something like that, you need to understand why. It may be as simple that your organization lacks a team to take on a shared responsibility. Or, more common, again, code changes for a reason. So the reason that code attracts 3 different teams is probably because it has too many responsibilities. So perhaps that code is better off split into 3. And while we have this data, why don't we overlay the result of a temporal coupling analysis? And that allows us to spot expensive change patterns, the kind that ripple through the organization. Remember the story I told you about a while ago, where a simple change took a week. Here's how we identify those change patterns. All right, we also talked about the communication diagrams. And when you do the communication diagrams, remember, they are created from how the code was built. What you will find is that there are just some developers who have made more contributions than others. Some people that work in virtually every part of the code base. These are core developers, these are key players, and they're probably quite important to your product or project. What if one of those people would leave? What if you would leave? What would happen? Well, we would probably get a knowledge gap. How big? Most of the time we have no idea. But using this data, we can actually find out. Here's what it looks like. So, you see those orange dots here? In this case, they don't represent any hotspots. No, they represent abandoned code. That is, code that's written by a programmer who's no longer in the organization. And this is something you can use as a team leader or technical manager to reason about the knowledge distribution in your system. And when you do that, what you will sometimes find is something like this. You have an entire abandoned subsystem. And again, that's something you can use for risk assessment. because it is an increased risk to modify code that you no longer understand. All right, I'm almost done now. I just want to sum it up for you. I think that these techniques will become mainstream within a few years. Our version control data is just the most underutilized informational data source we have in our industry. And we have seen some examples of the kind of value we can get out of it. We have seen how it helps us identify code that's hard to maintain, code at risk for defects, and code that becomes team productivity bottlenecks. And we've also seen that these techniques go beyond code and let us support organizational decisions around our systems. And this is a huge topic, and this presentation has really just scratched the surface. So if you want to dig deeper, please catch me afterwards. I'll be staying around for the rest of the conference, or have a look at my blog where I write about these topics. And yeah, of course, there's also the complete book that covers it in much more detail. And I also publish some open source tools that help you get started with these kind of analyses. Now, before I leave you, I just want to take the opportunity to say thanks a lot for listening to me, and may the code be with you. Thanks.